on this train. And you're just playing this guy, okay, this is kind of a see-through over here for the window. Don't worry about that detail. This is physics. So I'm playing billiards on the train. The question is, if the train is stopped, of course you assume it just progresses like an ordinary game of billiards. But if the train is moving, who thinks that that motion would affect how the balls would end up bouncing on each other?
Moving at constant velocity.
Yeah, so the train has begun moving, it is at a constant velocity. That's a very good question.
No, you should still be able to play. You should still be able to play like right.
Yeah, that's absolutely correct. And that's a fundamental principle of what we mean by relativity. What I mean when I say, okay, I'm not going to break here, but physics is velocity independent.
But then if the train like breaks suddenly, then it might mess up your other train, right?
Absolutely. It doesn't even have to break. If the train so much as speeds up a little bit, or maybe it goes around a curve or something. If I have a ball sitting on this table, and I suddenly jerk the table to the left, it's gonna, okay, my chalk isn't quite fluid enough, but if I flung it over here, you can imagine it would initially experience a little jolt to that direction of the table. Or, any kind of acceleration I can immediately detect with my billiard table physics lab. But it's a very profound idea. Another way of looking at it is, how fast do you guys think you're moving right now?
I'm not moving either.
Well, the Earth is rotating, so.
Relative to what?
Oh! What a question. Indeed. According to me, no, we got moving here. Come on, we're sitting down. What a silly question. Of course, if I'm standing on the North Pole even, maybe I'm doing a little twirly motion as the Earth rotates around in a circle, but I see you're whipping around the Earth. If I were to go to the sun, the whole Earth is just flying around the solar system at some crazy speed. You say you're not moving at all, but the sun thinks you're just flying all over the place. If I were on a different solar system, we think that our solar system is stable. The other solar system would look at us and say, God, everything's just flying around. It's entirely a matter of perspective and where you are, where you're looking. And no one's right. It's not, as long as we can all agree on who we're talking about, no one is the correct solar system. And I think that's a...
So I completely get this, but I have a problem with what you wrote. Speed of light is constant, the same for all observers. So
Yes.
that contradicts exactly what you've been talking about.
Thank you.
Either that is wrong, or it's just an approximation because speed of light is so big and it's such insignificant. You're moving at 50 miles an hour.
Thank you. Dare I say this leads into my topic of special relativity. And by the way, if you thought quantum mechanics is weird, special relativity gets crazy. It's amazing. So study it close. Yeah, absolutely. So just as we said, these two observers, the train versus me here, we're going to disagree on what the bullet's velocity is. I think it's 50 miles an hour, or sorry, you think it's 50 miles an hour, I think it's 100 miles an hour. And there's a fundamental disagreement. It's not like we disagree about what's going on. I could say, okay, I get it, you're in a train, so you think it's 50 miles an hour. It's not like we're fundamentally thinking something's inconsistent here. We just understand that we're moving relatively, and that's totally fine. But the statement that I'm saying, an axiom of special relativity, is that the speed of light is going to be seen as the same for all observers. And I want you to think about that, and what that means. And I'm going to give you 30 seconds, and I don't expect an answer, but if anyone happens to, and if you'd like to talk with your neighbor, that's totally fine. If anyone thinks they can come up with some kind of way of reconciling that, maybe some special velocity accomplishes that, or some other way out, then I'm very happy to hear it. That's all. Let's just think about this for 30 seconds, and you can talk to me. Yes, laser.
Right.
It would, what if you're moving it on the
It would
train
be
at the speed of light? I would still see.
So are we changing the mode to a height or are we going to train it?
Well, we're changing. Oh, we're talking about why light.
Okay. I know it's a really short amount of time, so I really was encouraging you guys to be able to dig into this incredibly meaty. But I'm kind of curious, does anyone have any ideas? Does anyone come up with some velocity or something special, way to reconcile this?
I have figured it out. No.
Move over Einstein.
Yeah, well, the two options that came to, at least to my mind was first that the speed of light is infinitely fast, and if it's infinitely fast, that no matter how fast you're going, it's gonna be always that speed. The second one is that the speed of light is, I don't know, you guys are gonna, I'm not obviously not a physicist. The second one is that the speed of light is traveling distances that are so far that are almost kind of like circular. So it's not. So it doesn't matter where you are. It's always going to be going at this speed because it's going so far and it's circular. That was one of the more BS.
I want you to dig into both of these.
Yeah.
So how about the first one first? Why would it being infinitely fast affect the situation? What's special about that? Or anyone can answer, it doesn't have to be, I don't know, it's fine. But why would the idea of, if my bullet, instead of going 100 miles an hour, if it was moving infinity miles an hour, how would that affect both of our perceptions?
Well, if it's infinite, you're going to see it the same. But
Why?
because
Infinity minus 50
infinity
is
is
still
infinity.
infinity minus 50 is still infinity.
Yeah.
Infinity minus 50 equals infinity. That's true. This is the maximum. This is a mathematical statement. Infinity's weird like that.
Yeah.
That's very good.
Although you have different sets of infinity, right? So
That's also true.
Unless it's
We are not going to begin to get into
Yeah.
which kind of infinity.
there are smaller and bigger infinities.
There are, and that's also really cool.
Yeah.
Yeah.
So the set of imaginary numbers is huge.
So, what about the other thing you said, the circular?
I don't know. I was still working on this process.
Okay. Any other ideas?
Well, no, I mean, I had that same impulse, like, maybe it's just coming from super, super far away and sort of never stops, but then not to, like, denigrate your idea, but then I thought about turning on a light bulb, and like off again, and so if it's like always constant the same, then the light that goes just a little distance would have to also be going really, really, or I don't know, going whatever speed it is that it goes, so that stopped making sense to me. After I thought about it.
Jason?
I don't want to get too far ahead, but in the example you gave us, right? If he fires a laser instead of a gun, then the speed of light is different for the guy on the train.
Is it?
That's where it gets.
Good observation. That is literally the point I'm trying to get across here. That is exactly the element that the claim of special relativity, the fundamental axiom of it, is that they both measure to be exactly the same. Even though exactly the same. There's no zero approximation to them. We assume that these are world-class scientists. Even though I'm holding a gun, I am an amazing scientist. And our measurements are perfect, and they are measurements utilize exactly the same.
Well, it seems to me that with some trend that the speed of light has to change because something else is moving. It has to do with our assumption that things like length and time are constant. That what we're measuring really is a measurement that's constant. That those things can't change, but if you can allow those things to change.
Are you trying to bring in our earlier discussion? How dare you? My goodness. Yes, indeed. So, on a very similar vein of what if we can play around with our measurement of position and time? Wouldn't that be one really weird way of trying to solve this? We're trying to measure velocity of the speed of light here. So we have to measure, if this is my laser gun instead of my bullet gun, we have to measure its distance traveled in some duration of time. So we have, our